Hello, everyone. My talk is about profiling and optimizing Go programs, and I have to say one thing in the beginning. You guys have too much coffee here, and that may be a problem because I probably drank too much, and also this stuff doesn't work. What should I do? Okay. Oh, no. Okay, whatever. So, if you can't understand me for some reason because I speak too fast or just too nervous, or you can't understand my accent at all, just read the slides. I put a lot of information here, and the most important stuff of this talk is also written, like in one sentence. So if you can keep one thing in mind, keep that everything is here. So, you probably know how to profile Go programs, right? You just wrote a program, it runs slow, and you just run prof tool and see something like that. And what you will do after that? I mean, probably if you see the stuff like that, you will be overwhelmed. You're not supposed to see this. When I told that everything is here, that's not it. But if you look closely, for some reason, you will see that the two blocks are probably too big, and you will see that this is our syscalls, and why the hell my program takes a lot of time in syscalls? It's supposed to switch to other routine. And what about this big block? Why in 30 seconds profile you will see a 20 seconds block, right? So this is not the way how you profile Go program. You can do it, you can try it, but in really you will not understand what's going on. It's just too late. So let's start from the beginning. So how do you actually profile your program? You have to start it before you have a problem. So the most important idea, you have to understand how your program works, how it performs before it's too late. Maybe your program is not optimized, but that's good enough for you. And then you will see a problem, you will see a difference between what was there before and what is now. And then you will understand what you have to profile. Maybe in simplest case, you can just roll back, for example. And you can also see that some new feature triggered a new code path, and you can roll back that or optimize it all in them because you know that before that your program was good enough. So how do we actually learn to use prof properly? Let's start from the very, very simple example. Let's say we have a simple cache, which basic interface like get me an element of the cache, set something, put something to the cache, and get the length, the amount of the elements in this cache. And let's write some very basic implementation. We use slice here, so when we get, we just iterate all over the elements. And when we set something, we will just check if element is here with this k already, and then set a value. And then no element is here, then we'll just append to the slice in the end. So who are you think that slice here is not a good data structure? Who will use something like map? One. Okay, quite a lot of people actually think that map is a good idea here, but why? What makes you think so? I mean, I said nothing about how this cache should be used, right? So maybe a slice is good enough in some cases. So let's test it. We will write a benchmark. This is a sample benchmark. We just set some elements to our cache, then reset a timer, and then get some elements of some IDs. IDs here is actually all the IDs in the sequence. So we'll get the first one, then second one, and so on. And all of that we'll get. So that way we don't have some optimization for slides when we get only the first element, which will be faster than map. And sync here, it's very important, but I will explain it later. So that's our benchmark. That's that green line is a map implementation, and blue line is slice implementation. As you can see, that slice performs better with a small amount of elements. And if this cache is for big objects, which takes a lot of time to build, but we have only a few of them, then slice might be a better idea. Especially if you are going. No, I mean, in that case, map is better when you have more than 6 or 7 elements. But before that, slice is slightly better. So when in doubt, use brute force, the simplest possible approach. What about sync? Why do we have to sync here, and why it's important how it works under the hood. So that's another problem that a former coworker of mine actually found, that a population count function, which basically just counts a number of 1 bits in uint64. So that's important function to run fast when you write some cryptography, for example. So that's the simplest version of that. We just make a loop and then check the current bit and increment by 1 when we found it. That's a black magic. You have a lot of constants, you have bit shifts, you have logical operations, but you don't have a loop here. And we assume that function will be faster because we know how processors works. We know that bit shifts are faster than just looping over some counter and so on. So how much faster it will be? Let's write a benchmark, right? Very simple benchmark. We just use a loop over bn, and actually that's the proper way to write a benchmark. Some people use bn as some argument to some function, and then they do not test for bn, but bn square, for example. The only way to use bn properly is using in a loop like that. So how much do you think the second version will be faster? Some wild guess. Twice, 10 times. Okay, so it's almost infinitely better for some reason. But when you look on this last number, it will take then like 1/3 of nanosecond per operation. You will understand that's very close to speed of light, actually. Something is very wrong here. It can't be just that fast, right? It's too fast. So how we can see it? What actually happens here? One way to see it is to run disassembler. I mean, actually run assembler, and it will see assembler output, right? We can get all the flags with go doc compile command, and then we have a C flag which shows us assembler output. Here's an important part. You will see that first assembler lines all have the same line number, and the last one is just a return from function. And what you see here, the first line is actually our for loop. You don't see any bit shifts, you don't see any logical operations, you don't see any constants here. You don't see our code here. It's only a benchmark code. So what's going on here? This function, it was very simple, right? It was a black magic, but from compiler point of view, it was simple. It was inlined, and then it noticed that function doesn't have any side effects, so it was compiled away. So the proper way to benchmark this code is to add some side effect. We assign the value returned by this function to some sync variable, which should be a global variable, and also probably should be an empty interface. So we always have some side effect, and compiler can't observe that this sync value is never used. The problem with sync actually is that it makes your test and your benchmarks running in parallel mode harder, but it's not really important for benchmarks. You shouldn't run them parallel in any way, but for tests, actually, you will have some race condition if you use sync in several of your tests. So maybe you should have several syncs in your house. Why not? So yeah, right now we see that second function is faster, about 50% faster, but not as fast as before. Sad. The other way to see what happens here is to run, to see all the internal compiler steps which compiler is running. Since some recent Go version, we have a static single assignment form of compiler, or SSA, and actually we can see all the steps compiler takes to compile on our function and make optimization. So let's see. Okay, so columns here are compiler steps, and you will see that yellow, this is our magical constant. Let's try to. Okay, it's pretty easy to notice here. And this line is actually our right shift operator. And if you scroll right, we'll see that after some stage called, after early dead code elimination stage, we don't have this constant and this logical operation anymore. So that's here where dead code is eliminated. We don't see our code anymore. Okay, so how to write the right benchmarks, right? Before we profile our code, we have to write proper benchmarks. We hear a lot of problems here. You should use async. You should not make sure that your functions are not optimized anyway. You also should not use virtual machine of any kind. I mean, even if you run your code in virtual machine in Docker containers or so on in production, when you benchmark, when you use profile, you optimize for throughput. You want your code to run as fast as possible when you profile. So you shouldn't use virtual machine of any kind. You should use a bare metal, and probably the kind of bare metal you will run in production. I mean, you shouldn't use, for example, profile on macOS. It has way too different characteristics from Linux you use on production. You also should not do anything on that machine when you benchmark. For example, if you run this test on your Linux notebook, you shouldn't run Firefox and browse some stuff here. While you wait, you will get a very, very different result. You also should disable CPU throttling of any kind. And again, on your development machine, it's most likely enabled by default. And when your processor is idle, it scales down the frequency, and you will get worse results. And when it's overheating, it scales down frequency too. So you will have problem both ways. And you have to use a benchstat tool which records previous version of benchmark output and compares them with current versions, and it shows you deltas and averages and so on. So you don't guess, you don't make your own calculations, you just use a tool and it will show you everything. So how do you use prof actually? You have two options. No, you have three options. You can use a runtime prof package or some version which uses that package to do some fancy stuff for you, and then you start a profile manually and then disable it before your program exits. You can use net HTTP prof package, which does some stuff for you. It registers a handler you can call to get a profile. You can use a go test command with some flags to run a profiler, and most importantly, you shouldn't do more than one things at once. And you shouldn't enable more than one profiler at once. So how a CPU profiler works? It uses setItimer C library call to receive seekprof signal every specified amount of time. So by default, you will get 100 invocations per second, and you can raise that to about 500 times per second. You can also change that value using a setCPU profile rate function, and then you run your benchmark and record output to profile file. What's important here is that up to 1.9 version of Go, which is going to be released in several days, you have to specify binary, because that prof output doesn't have symbols, and you will not get a valid result, and also you will not get a good error message in that case. You will just get some output, you will get a profile, but it will be missing some information, you will not understand what's going on here. So it's important to specify a binary. Or just wait a couple of days and you will get a new version that doesn't have this problem. So here, this is our simple slice-based cache, and you will see that it takes a lot of time in get function, which is expected. You will see that also it calls two runtime functions. First of it compares a body of memory if it's equal to some other body, and the other function is basically the same but optimized for string values. So when you compare, if we get the same ID as it was before, we compare previous and current IDs. If they equal, we replace the value. So yeah, you don't have a bad idea what's going on in get function, because it's a single function, it doesn't call any other thing, but it's more or less trivial to understand what's going on here, right? So when we replace that function with a map-based version, you will see that it uses some runtime functions. Two on the down is AES encryption functions, and they're very fast because they're basically implemented as a single assembler command, so it can't be optimized anymore. And also map access fast str function is optimized for string case and map. Also it optimized version for map in the runtime. So let's say we have a key, slice of bytes, and that would be slow. You will see that it uses a generic map of function, not the one optimized for strings. So here we can't probably optimize more, but when you have a different picture, you will get an idea that probably you should optimize something here. Okay, so what other kind of profiles we have? We have a memory profile, we have a block profile, we have a mutex profile. So the first one is profiles how much memory it allocates. So every allocation is, I mean, not every allocation, but some sample of allocation is profiled. Block profiler measures how much time you are blocked on something when you're waiting for some resource. A mutex profile is the opposite of block profiles. It records how much time mutex is held. So let's see. Let's say we have a new version of our cache. It's thread safe now, and we use a simple mutex to coordinate access to that cache, right? So that version is both set and get method thread safe. So we use a block profile here. We invoke it like that, and here I add a lines command just to show where in lines of code, not in just in function, we are blocked. So here we see that we take a lot of time in mutex, and that's not surprising, but that amount of time is probably too big for our problem, right? We should do something about it. And the easiest optimization is just to halt a read lock, not the big mutex, which doesn't allow you to do both reads and writes, because reads can be run in parallel. That's safe. And also we do a very small optimization here. We remove defer call, because defer allocates some memory, and we can save that memory. That's a tiny bit, but it's still important if we are going to use cache very heavily. Right, so after we run block profile here, we will not see that problem anymore, because in our benchmark, we benchmark on the get function, and that profile will not get any mutex, will not block anything. You can also use a custom profile. So what is profile anyway? Basically, profile is just a set of stack traces. And you can add some metadata to here, and I will talk about later, but you can also record your own stack traces. So when you have a situation where stack traces will be useful, you could use a custom profiles. One good example that, let's say you're tracking some outgoing connections or some open files, and you want to know where those files were opened and where you should close them, right? So you record a profile every time you open a connection or file, and then mark this profile, remove this profile when you've closed the file. And you have this new profile and lookups method to create your profiles, and recommended practice here to avoid a collision to have an import path as your prefix for your profile, and that actually doesn't work because they have a bug, and it doesn't work correctly with slashes in this case. So the simple solution is just to replace slashes with underscores or something like that. You can also add the custom labels to your profiles. So what is it? It's basically just a key-value pairs you can add to your stack traces. For example, you can use URLs in your API application or SQL queries if you're doing database. And then you will see them in the profile in both in WebView and console line application. You can filter by that. It's not released yet, but yeah, it's going to be released in several days. Very cool stuff. And next version, we will get even better stuff. We'll have some fancy UI for prof. It will allow you to focus on something. You will also get labels. You will be able to filter, and yeah, very cool. It actually works now, so you can get a tip version and then bundle Google profile on top of one prof provided by Go. What's next? Yeah, Ivan already mentioned execution tracer. So execution tracer records all the events you have in, like routine, starting, stopping, switching, blocking on anything, blocking on select, waiting for some condition. Unfortunately, it doesn't include yet blocking on sending and receiving from a channel. But you can apply patch, and you will get that too. What's important here is that all the events are recorded, and that file is actually will be quite big. It's not very easy to work with it. As again, as the one mentioned, your browser just hung when you try to open the whole tracer output. Some recent Go version started to actually how to say it, split this big file to 2 seconds interval. So you will not be able to open the whole thing at once. You will get only 2 seconds, but then you can scroll and skip to the next interval. It will have quite a high overhead. So if you're going to run this on production, you probably should not do it on every second backend you have, but for single or for 2 backends, it will be fine. And also you have to understand when do you need to use tracer, when do you need to use prof. So tracer is for tracking the throughput, and I mean prof is for tracking the throughput, and tracer when you want to optimize for latency, not for the maximum speed, but for the maximum response time. So how do you use it? You import a net HTTP prof package, and then you will also get this debug prof output. And then for that example, I wrote a single network cache, which looks like Redis. It implements a Redis protocol. And then I use a Redis benchmark to load it. Yeah, and let's see how it looks like. Okay. So here we have first line is our heap, our memory allocations. The second one is number of goroutines we are running. We are having our number of goroutines is moving down in that case because that's when some benchmarks are stopping, and basically that's the last seconds of running a benchmark. Here we have an amount of threads, and then we have our Go code running on processes. Yeah, so proc here is a GoMax procs basically instance. It's a CPU core or something like that. Here I have GoMax procs at 4, so here we have a 4 procs. The first one is empty here because it has doing some network stuff on the right, so you don't see it here. You will see a lot of small reads, hopefully. So all the small reads are doing from boof.io package. So here I made some small optimization and not actually reading from the network at once, but using a boof.io. But you will see that there are a lot of small reads. So that's because how Redis protocol is designed. It basically starts with a length. It gets you 4 bytes of length, and then you will allocate some memory, and they'll read the whole package here after this 4 bytes. But I'm using a small case here, and basically our comments are small, so we have a lot of small reads. What we can do here? Actually, not much. I mean, if we had not had the small optimization and try to read by 1 byte, for example, you will see there are much more reads and they are much more smaller. We can try to read more at once, but in our case, it will not help. If we had big packages and we will have like a set of massive sets, like sets in megabytes at once, you will see that our allocations are large and our reads are large, and then we will probably should reduce a number of allocations by allocation less. But at least you can see what's inside, how your runtime works, and how your program what is your program is actually doing. Okay, so yeah, that execution profile is not very easy to deal with. It's large, and that UI interface is actually very confusing when you try to use it like first time or second time, and probably you're not going to use it after that because it's too hard. So I guess science last Go version have go to trace prof command, which basically converts this trace output to prof kind output. And most importantly, it also adds symbols to this profile, so you don't have to add a binary when you analyze this profile anymore. And this type can be a net, sync, syscall, or shed, depending on what you want, and maybe some other types will be added. So for example, when I add this net flag here, you will see that you will see all the network commands. It's very useful if you think that some problem is with your network. For me, the most important thing of optimizing your program is understanding how operation system works and how Linux works if you use Linux. And you can use system profile tools, and perf is the most important one. I guess anyone who ever tried to optimize Linux knows how it works. It wasn't possible to use perf with Go programs some time ago because Go did not have stack frame pointers, I guess. Yeah, and since some version it has them, so you will get the good stacks with perf. It will actually work. It was possible to use it with systemtab, but systemtab is going to be removed from Linux kernel, and the new thing in Linux kernel is BPF, which stands for Berkeley Packet Filters, and how it's related to performance and why do you have a Berkeley Packet Filters is basically what AP tables uses. That's because they expanded it a lot, and now it's more like a dtrace in Linux. So you can do a lot of stuff with that. You can add dynamic traces, you can watch for some dynamic events, and very cool stuff. And it has some Go integration. It's not very stable yet. You can crash your program easily, but you can, if you're lucky, you can also trace it. How to understand what's going inside of runtime without using a tracers? You can set a GoGC variable which allow you to disable garbage collector completely, and we will see if that problem is because you allocate a lot of memory or your memory is too fragmented and something like that. If you allocate a lot of memory, your program will not survive for long. The kernel is going to kill it. But if it works, and then you will understand the problem is somewhere else. And also you have a Go debug variable, which allows you to set a lot of stuff. The most important one is when you disable some network issues and you don't understand why your host name is not being resolved. That's because it uses either Go DNS resolver or C-based resolver from system, and they work somewhat differently. So it's good to know about Go debug variable for that, but when you profile, you have some other flags. For example, you see a GC trace, which outputs a line in stdout every time a garbage collector runs, and it will show you some output, and you can parse it and send to your monitoring system. You have a log-free trace, which traces every single allocation and free call, and you will get a lot of output from that. But again, you can store in file filter by some condition, just grep, and then it will help you to see a problem. And shed trace, it shows in that variant, it will show you every second some statistics from scheduler when scheduler moves your coroutines to other threads and so on. And if you see that there are a lot of moves that you probably run too many coroutines, you're starving on CPU power. You have to run more cores, more CPU threads than you have. And some very basic spot optimizations you should keep in mind when you write your code. So I don't know if you know or not. Let's guess how much memory the first empty struct takes. Anyone knows? How? 30. Actually 0. So that empty struct doesn't really allocate anything. And why do you want to use it? When it's useful? Well, you can send that value over the channel as a signal mechanism if you want to have two different mechanisms for channel. You can close a channel, or you can send an empty struct. Or you can use it as a set. For example, you can make a set out of map when your key, some string or what you want, and the value is tracked. And some people prefer to use bools. By my personal recommendation is to use struct, because with bools you have actually three states, right? So you have an absence of key, that means that value is not in set. You have a true, which means that value is in set. And you have a false, which I'm not sure what this means. I mean, it's different from both absence of key and true. And with empty struct, it makes sense. So you have a struct here, then you have a value. Then let's say you have a some map where string is a key and you have a slice of bytes. And if you write access to this map as written here, exactly as that, it will not allocate a string. It will just use the slice of byte to make a temporary string without actually making it. It's optimized in compiler. When you refactor this code and say you want to extract this into temporary variable, you will lose that optimization. So it's important to remember that. The next one, when you iterate over a string and you want to iterate over each byte as opposed to each UTF rune in string, and you, again, if you make like a temporary slice of bytes, it will not actually allocate anything to. It will just iterate over every single byte of string, and there is no way for you to change that. So that string is still immutable, so it's possible for compiler to optimize that. And if you want to fill some slice or some array with 0 values before, like, let's say you use some slice and you want to keep that allocated memory, that capacity of slice, but you want to pass it to some other function and it doesn't have access to previous data in that slice, you can fill that with 0 values. And that simple construction is optimized at a single mem0 call in runtime. Again, if you try to change something here, if you try to do it over map, for example, if you use a not 0 value, it will not be optimized. And let's say you are making a cache again. I like caches. So let's say you have some map, and as a key you have an array of bytes, not a slice, but array. And as a value, you store values here, not pointers. And inside that struct is array and some integer values. So there are no pointer inside, and you have a huge map, and it will be completely skipped by garbage collector. Because compiler knows that there are no pointers here, it will not try to check all the pointers to mark what should be removed and try to remove it. So it is possible to make a very effective cache that way. But if you add some string here, you will get completely different performance characteristics. So that's why we use array. So that's basically it. So the most important thing to remember is optimize and profile your code before it's too late, before you understand how your code works, not when you have a performance problem. And learn Go and prosper. Thank you.
Questions, please?
What about famous proverb that premature optimization is the root of all evil?
That guy is famous too.
Yep.
Well, basically I'm not saying that you should optimize your program right away, but you should understand how it works. It's a big difference.
Fair enough. Thanks.
So thanks to Alexey. Now we have time for coffee break, about 20 minutes.